Good day, Physics 1000 students. This is going to be the video lecture for the Chapter 3 notes. Chapter 3 is going to be about rotational motion. Up until this point, we have been looking at the universe, looking at motion in terms of just moving forwards or backwards in one, maybe two different axes at once. We live in a three-dimensional universe, and one way in which we are able to differentiate one place from another place is by tracking how far those 2 points apart in terms of x, y, and z coordinates, forwards, up, and, in and out, length, width, and height. But there is a different method that physicists use sometimes for explaining motion, namely rotational motion. Because not only can objects move forwards and backwards in one of three directions, they can also rotate. They can roll or spin about a central point. And this is a different type of motion that requires us to examine in different ways. As a matter of fact, rotational motion can be considered to sort of be, sometimes we call it a parallel universe to linear motion, because all of the formulas and principles that we have been talking about for linear motion, and linear motion is what we've been doing so far, where something is just moving forwards and backwards, it is displacing some number of meters in a direction. Every principle for linear motion has a counterpart in the rotational world. I'll begin explaining now. So, linearly, if something is just moving linearly back and forth, it is moving some x displacement, and we measure that in meters. But, in addition to whether or not an object is simply moving around in three-dimensional space, it could also be spinning. And the way that we measure this rotational motion is, instead of using meters, because meters is a measure of, the physical straight line distance between things, for rotation we look at radians. How many radians has something traveled around this circle? Radians is very similar to degrees. So like feet and meters measure the same thing. They're both units of length. Radians and degrees both measure rotational displacement. How far have you rotated? And some things to be aware of. One full rotation is equal to 360 degrees. And one full rotation is also equal to 2 pi radians. Radians are just a different measure of angle. So I'm going to demonstrate this, if my actual demo will stay intact. I'm going to demo this with an umbrella. And I have put a sticky note on this umbrella so that you can more easily track its rotation. So right now this sticky note is straight up. It is on the very top of this umbrella. As I begin rotating this umbrella, so let's say I'm going to turn it 90 degrees, that sticky note has rotated 90 degrees from where it started, even though the umbrella, as it's rotating, the umbrella is not really going anywhere. The umbrella is staying in one spot, and the sticky note is going to keep falling off. So I just got to fix that. So, the umbrella is not going anywhere. The umbrella is not actually moving linearly. But it is rotating. And we can tell it is rotating because we can see it rotating. We can watch the sticky note as it moves around. If we're starting from here, then this would be a 90-degree rotation. The umbrella has moved 90 degrees from where it started. I'm actually going to put the sticky note here so it's easier to see against the whole of the umbrella. So we begin here, we rotate 90 degrees to here, 90 more degrees puts us here. This is a total of 180 degrees displacement from where we started. This is rotational displacement. Now we're at 270 degrees of rotational displacement, and now we have rotated 360 degrees. So one full circle is always 360 degrees, and we are just watching this umbrella as it is rotating through that displacement. So the measure of degrees that something has spun is a measure of rotational motion. It is a measure of angular displacement. I'll write that term up on the board. Angular displacement. Now, angular is just a fancy science way of saying rotational. If any concept has the word angular in front of it, you know that that concept is going to be of or relating to rotational motion. So, as we watch this umbrella spin, it is displacing. So, linear displacement means it's moving forwards, backwards, some amount of meters. This is not linearly displacing because the umbrella is not actually going anywhere. The umbrella is staying in the same spot of space, but it is rotating. It is angularly displacing by some amount of degrees as it spins. And we're going to be using units of radians a lot for this particular topic. Radians is the more metric version. Degrees and radians measure the same thing. They're like feet and meters, but we're going to be using radians. Now, 360 degrees, one full rotation, equals 2 pi radians. So, here's my sticky note. If we start from here and we rotate 90 degrees, this rotation would be pi over 2, half a pi's worth of radians. That's not half of a radian, that's half of pi. Pi over 2 radians. Next, if we go down here, from beginning to end, we've rotated 180 degrees. From beginning to end, that's 180. That would be pi radians. Next, this is going to be 270 degrees from where we started. This would be 3 over 2 times pi radians. 3 times pi over 2 radians. And then last, 360 degrees. We've done a full rotation from where we started. This would be 2 pi radians. 360 degrees equals 2 pi radians. So this is a conversion factor that you can use to go between degrees and radians. And so, this set of notes are going to be talking about the angular world, because just like objects can displace both linearly if they are moving back and forth, and angularly if they are spinning, every concept related to linear motion has some version in the angular space. If you can move angularly, you can also have an angular velocity. If you can if you can have a velocity linearly, you can also have a velocity angularly. You know, if you are moving back and forth at 5 meters per second, you can also spin at an approximate speed as well. And if you can have an angular velocity that can change, therefore you must be able to have an angular acceleration. And that's what the next couple slides are going to be about. Slide 1 on the notes is the title slide. Slide 2 introduces this concept of rotational motion. Give this a look. Something to keep in mind from this particular slide, we use delta x to describe linear displacement, but we're going to use delta theta to to describe rotational or angular displacement. This is the Greek letter theta. Very frequently it is used to represent, a number of degrees in a triangle drawing. It's the same sort of thing here. It's the number of degrees, the number of radians that you have elapsed from your starting point. I'm just going to clear the board real quick so that I can start putting things up in terms of comparing them to their, so we can compare these angular quantities, these rotational quantities, to their normal linear counterpart. So, we have the linear world and we have the angular world. In the linear world, we have displacement, velocity, and acceleration. These are the three vectors that we have used to describe linear motion. We can use these to describe where everything is and how it is moving in 3D space. Now we're going to begin comparing them to their angular counterparts. The angular counterpart to displacement is angular displacement. We measure that with a theta. Next, slide number 3 now, we have angular speed or angular velocity. Now, originally, linearly, velocity is equal to delta x over delta t. Angularly, the symbol for angular velocity, this represents the speed at which something rotates. So, right now I'm rotating the umbrella very slowly. This is one specific angular speed. If I rotate it a lot faster, this is now a different angular speed. So the angular speed represents how fast are you rotating. That's all it means. So, the symbol for the angular speed is omega. This is a lowercase omega. I'm sure most of you have probably seen an uppercase omega before. These are both Greek letters. This is lowercase Greek omega and uppercase Greek omega. Uppercase Greek omega famously looks like an upside-down horseshoe. Lowercase Greek omega kind of looks like a squiggly W. It also kind of looks like, I see it as a mustache. But this omega represents angular velocity. And the way that we find angular velocity, so normally linear velocity, you take linear displacement and divide it by time. For angular velocity, you're going to take angular displacement and divide it by time. So the same logic still applies. Velocity is still displacement over time. You just have to look at, are you displacing linearly or displacing angularly? But the same logic applies. It's really the same formula for each. You're just subbing out linear for angular. And then if you move on to slide 4, you'll see the same thing for acceleration. Now normally, acceleration is equal to change in velocity over change in time. The symbol for angular acceleration, this one's a little harder to differentiate at first. This, it kind of looks like a fish or a cursive A. This is a lowercase Greek alpha. In Greek, uppercase alpha is really just an A. Lowercase alpha is this fancy kind of script A with an extra tail on it. It kind of looks like a fish, so some people just call it fish. But this represents angular acceleration. And normal acceleration is defined as the rate and change, the change in velocity over time. The same logic is going to apply. So, angular acceleration is going to be equal to angular velocity, the change in angular velocity over time. It's the same logic, it's the same formulas, you're just changing which set you're looking at. And so, the reason we sort of call these parallel universes is all the logic still holds true. Everything has an exact counterpart on the other side. It's just something's a little bit different. It's like the old episode of Star Trek where you would go to the parallel universe and like everyone has a mirror counterpart that's just slightly off. It's the same thing here. They're all the same, but just tiny little bit different in the way that you are looking at spinning instead of moving forwards. And if you look onto the slide number 5, there's further evidence of this and a couple extra formulas. Now, linearly, we have been looking at our Fantastic Four equations. We've got 2 of them up on the board already. V equals delta x over t, A equals delta v over t. I'm going to put the other 2 Fantastic Four equations up here, the ones that we're used to, in their linear forms. So these are the equations we are used to, and they have angular dimension. They have angular counterparts as well. You're just going to take all of the linear versions of everything and replace it with its angular counterpart. So linearly, we have delta x equals v naught times t plus 1/2 at squared. Angularly, we're going to have delta angular displacement equals initial angular velocity times time plus 1/2 times angular acceleration times time squared. And for the other formula, instead of normal linear final velocity, we're going to have angular final velocity squared equals angular initial velocity squared plus 2 times angular acceleration times angular displacement. It's the same formula. There's just, you've just changed which specific thing you're looking at. It's sort of like instead of, all of these had meters in them before. X is measured in meters, velocity is meters per second, acceleration is meters per second squared. All that's really happened is, instead of looking at meters traveled in a straight line, you're looking at radians rotated. Radians rotated. And to help facilitate converting back and forth between these two worlds, there are some additional formulas that we have available to us to help us convert. And those formulas, they're listed in the middle there. So I'm going to put them in the middle here also. I'm going to make one teeny tiny alteration. So everything in the middle, in the purple, is the translation formula, the way we are able to convert between linear and angular. Because, as it happens, objects that are rotating are moving in three-dimensional space. So when I spin this umbrella around, even though the center of the umbrella is not traveling, all of the spokes on the outside of the umbrella are still moving. Where's my sticky note? If my sticky note starts up here and I rotate 90 degrees, that sticky note has traveled down linearly from where it started and out horizontally from where it started. So even though it is angularly rotating, it's moving through linear space at the same time. It is possible for an object to be doing both. And the way that we convert from one to the other is by using the radius, so the R here represents radius of the actual rotation. So, brief vocabulary to help everyone remember. The radius of a circle is the distance between its edge and its center. Between its edge and its center. So if I'm going to take my handy-dandy meter stick meter sword, and I'm going to try to measure the radius from the center of my umbrella to the sticky note, looks like that's about, might help if I was starting from the right end of the meter stick. Yep, it looks like about 50 centimeters. 50 centimeters. So the radius between here to the sticky note is 50 centimeters. And that radius determines how much it's going to move linearly as it rotates. Now the radius is important because right now the sticky note is at the edge of the umbrella. But what I'm going to do is I'm going to take a second sticky note and I'm going to put it closer to the center of the umbrella. So now we've got two sticky notes here together at once. Now, if I rotate the umbrella by 90 degrees again, both sticky notes, sorry about that everyone, I should get a fresh sticky note. It's still sticky. So, as I rotate this umbrella with the... Are you kidding me? I should know better than to try to put sticky notes on a curved umbrella with a material made of a material designed to resist things sticking to it. It is the point of an umbrella, it's to keep water off of it. I'm going to use some tape. While I'm futzing with this, I hope you're all having a great day. Enjoy this brief intermission. All right. So, if I rotate the umbrella 90 degrees, each sticky note is going to rotate 90 degrees. Their angular displacements are going to be the same, 90 degrees each. But they're at different radii from the center. I'm going to say this first sticky note is about 25 centimeters from the center. The second sticky note is about 50 centimeters from the center. If I rotate them both 90 degrees, notice the distance this sticky note traveled from here to here is greater linearly than the distance this sticky note traveled from here to here. This distance is much smaller than this distance. Whoops. So even though their angular rotations are the same, angular displacements are the same, they have different linear displacements. And it's all because of their radius. So, knowing your radius of rotation is important because it will help you translate linear to angular and vice versa. And moving on to slide 6. Okay, so moving on to our example on slide number 6. We have a grasshopper sitting on the very edge of a record player. Now the record on the record player has a radius of 20 centimeters. The grasshopper is at the very edge of the record, so that means the grasshopper is 20 centimeters away from the center of the record. That means the radius of rotation for the grasshopper is going to be 20 centimeters. Now, this record player eventually is beginning its initial velocity, its initial angular velocity is 0. It is starting from rest. So, it is starting from rest, so its initial angular velocity is 0. And we measure angular velocity in radians per second. it tells us that after a time of 3 seconds, so delta t is going to be 3 seconds, after 3 seconds, the player is going to have sped up to a final angular velocity of 45 revolutions per minute. Revolutions per minute. Now, before we do anything else, revolutions per minute is not our standard unit. Our standard unit for angular displacement is going to be radians, not revolutions, and our standard unit for time is going to be seconds, not minutes. So we need to convert this revolutions per minute into radians per second. So, I'm just going to rewrite this a little bit. Revolutions per minute. And now we're going to translate it. So, first let's go ahead and turn minutes into seconds, because everyone should know 1 minute contains 60 seconds. So putting 1 minute, multiplying by 1 minute over 60 seconds will cancel minutes and leave us with seconds on the bottom. Next, one full revolution, that means one whole turn of the wheel from start all the way around to finish. That's a 360-degree turn, which means one revolution contains 2 pi radians. And so this will allow us to successfully convert from revolutions per minute into radians per second. I'm going to get out my calculator and show you how I enter this. You got 45 times 1 divided by 60 times 2 pi divided by 1. And at least on my calculator, I do have a function for pi. I access it by hitting the second button, and then there's a little pi symbol above this caret sign here. I presume if you all have different calculators, that's fine. Just know how to be able to access the pi function on your calculator model. If I press enter, that's going to give us the angular speed in radians per second. So, our angular speed in radians per second is 4.71 radians per second. So that is our final angular speed. That is the angular speed that we are getting up to. And that is the answer to the first question on the slide. What is the final angular speed of the player and the grasshopper in radians per second? So we have already answered question 1. Great job, everyone. Next question. What is the angular acceleration of the player? The player is changing angular speeds. Originally it wasn't rotating at all. Now it is rotating at this rate. So we need to calculate its angular acceleration. Formula for angular acceleration, we can pull this from the formulas we were just looking at, the angular counterpart to the acceleration formula. Regular acceleration is change in velocity over time. Angular acceleration is going to be change in angular velocity over time. So, our angular velocity final is 4.71 radians per second. Its initial was 0. Delta always means final minus initial. Final, we already know delta t is equal to 3 seconds. 3 seconds passed as this happened. And so, now we just have to divide 4.71 by 3. Which will give us 1.57 radians per second squared. Radians per second squared. And so that is the angular acceleration of the system. That means every single second that passed, the record player became 1.57 radians per second faster. Next question. What is the linear acceleration of the grasshopper? Even though the grasshopper is rotating, it's still moving through three-dimensional space, just like the sticky notes on my umbrella. It's still moving through linear space, so we need to be able to find its linear acceleration as well. Now this part here, we are going to be translating this angular quantity into its linear counterpart. And we have formulas for taking something linear and turning it into something angular, and vice versa. Those are the formulas in the middle, the translational formulas. The one for acceleration says linear acceleration equals angular acceleration times the radius of rotation. Now we want the linear acceleration, so we just need to plug in radius and angular acceleration. Our radius is 20 centimeters, but centimeters is not our standard unit for length. We want meters. So we will need to convert 20 centimeters to meters. 1 meter is equal to 100 centimeters. Therefore, to convert this radius, we're going to divide it by 100. So 20 centimeters is going to be 0.2 meters. Make sure you can do that conversion. And the angular acceleration is what we just found, 1.57. And that, multiply those two things together, that will tell us the linear acceleration, which is 0.314 meters per second squared. So, as the grasshopper is spinning around, its linear velocity is changing by this amount as it spins around. If the grasshopper was standing at a different spot on the turntable, the radius would be different, and that would change this acceleration. Now notice, the r is being multiplied by the angular acceleration. That means the bigger the radius is, the more your linear acceleration is. The farther you are away from the center of the orbiting object, the rotating object, the more acceleration you are undergoing. The faster and faster you will eventually get, linearly speaking. And this is why, if you've ever played on a like the sort of merry-go-rounds on children's playgrounds where someone else outside of it grabs it and spins it, and every kid is just trying to hang on to it. If you've ever noticed that it's harder to hang on the edge versus in the center, this is why. Now, last question on this slide. If the grasshopper lets go after 5 seconds, what will be the linear speed of the grasshopper? Now, this grasshopper is on the edge of the turntable. It's on the edge of the disc. It is spinning around. It's eventually going to reach the top angular speed of 4.71 radians per second. It's going to reach that top speed at 3 seconds. So by the time we hit 5 seconds, we're already moving at this angular speed. So 5 seconds after the beginning, this is the grasshopper's angular speed. Now, we know it's at the 20 centimeter mark, so we can find the linear counterpart to this angular speed. The formula to translate linear velocity from angular velocity is linear velocity equals r times angular velocity. So our radius is still 20 centimeters. That's 0.2 meters. Our angular velocity that we will be moving at the 5 second countdown mark is 4.71. And so the linear speed that the grasshopper is going to be moving at the 5 second time mark is 0.942 meters per second. Now what this represents is, if the grasshopper let go of the wheel right now at 5 seconds, it would shoot off in a straight line at this speed. Once it lets go of the wheel is not forcing it to keep moving in a circle. It has already built up this linear velocity. The wheel is just forcing it to keep moving in a circle. But if it lets go of the wheel, it's no longer being forced to move in a circle. So instead, it will begin moving in a straight line. And this is, well, for one thing, this is how baseball pitching machines usually work. A baseball will sort of get stuck inside of a wheel, and it'll spin and spin and spin until it gets fast. Then the wheel's going to let go of the baseball, and the baseball is going to shoot out of it in a straight line. The only thing that's keeping the grasshopper moving in a circle is the wheel. If it's not attached to the wheel, it's going to move in a straight line, because matter actually prefers to do that. Newton's first law says an object in motion will remain in motion. And so it now has this linear velocity. If it lets go of the wheel, it's going to keep moving at this linear velocity. It's just going to do it by shooting away from the wheel in a straight line. We'll talk more about this in just a sec. So moving on to slide 7, we're going to explain more sort of the phenomena of the difference between the cricket holding on to the disc versus letting go. Now there is something to note. There's sort of a minor difference between whether or not one object is just rotating. So right now we can just look at the umbrella as an object that is rotating about its center axis. But we can also look at the sticky note as a separate object that is orbiting around the center of the umbrella. So both objects are rotating. They both have the same rotational tendencies right now. They have the same angular speed, same angular acceleration. But the umbrella is one single object that is rotating about its own center axis. Meanwhile, the sticky note is a separate object that is being held and forced by some outside phenomena to continue moving in this circle. If the sticky note, so right now I've got the sticky note taped to the umbrella. If this was just a normal piece of paper that I just held right here and I then began spinning, if it's just normal paper without any tape, without any sticky adhesive material, there's not going to be anything keeping the sticky note on the umbrella. Therefore, the sticky note's not actually going to rotate if it's not stuck to the umbrella. There has to be some force keeping the sticky note to the umbrella, keeping it moving in this orbital pattern in order for it to actually do so. And if you move on to slide 7, the specific thing that is causing that to happen is called centripetal force. Now, to best understand the definition of centripetal force, we're going to look at the root words that make up the word centripetal. The word centri means center, and the word petal means seeking. So centripetal force is the center-seeking force. It's the force that pulls an object towards the center of its orbit. So, when the cricket is gripping the record, there's a force pulling the cricket towards the center of the record. Now the cricket has a tangential linear velocity. If the cricket was not holding on to the record, it would shoot off at this velocity. But because it is holding on to the record, there's going to be a force pulling the cricket towards the center of the record. And that's going to cause the cricket to accelerate towards the center of the record while it still tries to move forwards. Now, because it's doing both at the same time, the centripetal force is going to cause a centripetal acceleration. So centripetal force causes centripetal acceleration. The cricket is gripping onto the record. That force, that centripetal force, is going to cause the cricket to centripetally accelerate towards the center of the disc. It's going to accelerate towards the center at the same time as it is firing off into the distance. And as a result of doing both at once, the cricket's not going to go just towards the center of the record. It's not just going to go out in this direction. It's going to do both at once. And it's going to end up over here. So it went forwards and it moved towards the center at the same time. And as a result, it just spun around the arc of the record. Now, centripetal force is always center seeking. It's always pointing towards the center of the circle. So it's not pointing in the same direction anymore. Now it's pointing at this angle, but still towards the center. And meanwhile, because the cricket has accelerated around the circle, its direction has changed. That means its velocity has changed. Its new tangential velocity is now pointing this way. Its velocity has changed directions. So since both vectors, the centripetal acceleration and the tangential velocity, have both changed, now the cricket wants to go this way, the centripetal force is pulling it this way, and so it's going to sort of do both at the same time and continue moving around the arc length. So, centripetal force is what makes an object orbit about some other point. A further demonstration of this. I have here, this is just one of the stringiest objects I have in my office right now. It's just a charging cable for my phone. And I am going to, this is a roll of tape, tie this roll of tape at the end of it. Now, if I was to spin this object around in a circle, there is a force from the cable that is always pulling the tape towards the center of this orbit. The tape is sort of moving both angularly and linearly at the same time. It is moving angularly about this central point, but it's still moving linearly through 3D space. It's moving up and down in the vertical axis and side to side in the horizontal axis. And the force from the cable is the only thing that is actively keeping the tape moving in this circular shape. If the cable just stopped, if the knot came undone, if the knot was to come undone, then at the moment it came undone, the tape would just keep moving in the direction of its tangential velocity. Notice that word tangential. It means tangent to the circle. All of these velocities that I've been drawing are tangent, meaning they only touch the circle at one point. They are tangent to the surface of the circle. So, if a force is acting as a centripetal force and acting on an object that is moving, notice nothing is happening if this particular roll of tape is not moving. It is only when the force from the cable is pulling the tape towards the center and the tape has a velocity. When both of those conditions are met, the centripetal force, the cable can act as a centripetal force and force the tape to move in an orbital pattern around the center of this rotation. Now the thing with centripetal force is, you've all felt it. You have all interacted with centripetal force before. Pretty famously when you are driving. If you are driving a car and you turn left, you have angled your wheels, you have angled the wheels between your car and the ground in such a way that the friction, so you were moving forwards, your car was driving forwards, but you have now changed the angle of your tires so that the friction from your tires and the road is now pointing that way. Your car was moving north. Now the friction from your tires is accelerating you west. You're still moving north though, so you're going to begin spinning around an arc. And as long as you keep the wheel turned like that, the friction is always going to point to the left of the car. But, you know, what your left is always changing. It's always going to point towards the center of your movement. And so every single time you turn your car, you're actually just entering into part of a circle. When you when you are turning your car as you are driving, this arc length here is just part of a bigger circle, and the friction from your tires is acting as a centripetal force to cause your car to orbit about the center of that circle. But when you get to this point here and you want to go straight again, you turn your wheels back to normal. Now the friction between your tires and the road is not pointing to the center. Now it's back to normal. And now there's no longer a centripetal force pulling you towards the center, and you keep driving forwards. So, centripetal force is what makes objects orbit around some central point outside of themselves. You see this when you're driving. You see this on roller coasters. You see this if you tie something to the end of the string and spin it. You also see this in space. So let's look at the Earth and the Moon. The Moon orbits around the Earth, which is good. We need the Moon. Keeps our tides moving. The Moon orbits around the Earth, but why? There's a force between the Earth and the Moon that acts as a centripetal force to keep it moving like this. And that force is actually gravity. There's a gravitational force between the Earth and the Moon. The Earth is pulling the Moon towards it. It's exerting that gravitational force. So, here, the force of gravity is acting as a centripetal force. The Moon has a tangential velocity. It wants to be going this way, but the Earth is pulling the Moon towards it. And so as it tries to move in this direction, it begins accelerating towards the Earth, and it just begins moving in a circle as long as Earth's gravity is affecting it and as long as the Moon maintains its tangential velocity. If the Earth was not here, if there was no force of gravity, the Moon would just move in a straight line because it needs Earth's gravity to act as a centripetal force to keep it rotating around the Earth. All centripetal forces are caused by existing forces which act as the centripetal force. For the tape on a rope, it is the tension in the rope that acts as a centripetal force. For moons and planets orbiting some other object, it's the force of gravity. When you are turning your car, it's the force of friction. There's always an existing force that acts as the centripetal force that makes this happen. And I'm going to go ahead and put the formulas for this up on the board so that we can use them in a sample question. So, the total centripetal force, this is F sub c, centripetal force, acting upon an object is equal to the object's mass times its centripetal acceleration. Centripetal force causes a centripetal acceleration. And the centripetal acceleration of an object is equal to linear velocity squared over orbital radius, or alternatively, an equally valid formula is angular velocity squared times radius. Both of these formulas mean centripetal acceleration. And these formulas will allow you to be able to calculate the centripetal acceleration in a system, or alternatively, if you know the centripetal acceleration, you can find how fast an object is orbiting. And we're going to work some examples related to this now on slide 8. So slide number 8 is an example, pretty famous case of weaponized centripetal force. Instead of a cricket on a disc, this is going to be an example a little bit more like the tape on my cable here. David is about to fight Goliath. He has a sling, and a sling with a rock in it is basically the same thing as I have here. It's just a rock on a string, and you spin the string around to get the rock up to some speed. And when you want to release the sling, you just let go of the rope, and at that point the rock will fly off in the tangent direction it was just moving when you let go. So you just spin the sling around, you release it, and your projectile flies forward. So, we have a sling in this example. The sling begins at rest. What that means is all of its velocities begin at 0. Its linear velocity begins at 0. Its angular velocity begins at 0. We know that from the fact that it begins at rest. We also know the radius of this sling. The problem says it is 35 centimeters. I'm going to go ahead and convert that to meters because we like all of our units to be in, we like all of our displacement units to be in meters. So this is the radius of the slingshot. And it took 1.5 seconds to get the sling spinning up to the speed that David wanted it. So our delta T is 1.5. We also know mass of the rock. Mass of the rock is 300 grams. I'm going to go ahead and convert that to kilograms. It's going to be 0.3 kilograms. And the sling's final linear velocity, this is the velocity that it took off at in a straight line, is equal to 50 meters per second. This is its final linear velocity. So, first question. What was the tangential linear acceleration of the stone at 1.5 seconds? Well, what is the linear tangential acceleration of the stone during this amount of time? So, what we want is linear acceleration. That's just A. Acceleration is defined as the change in velocity over time. We know the final linear velocity, the initial linear velocity, and the time. So, one formula that contains all of those things, A equals delta V over delta T. So, we got the sling up to 50. It began at 0. This whole thing took 1.5 seconds. This can tell us that the linear acceleration of the rock during this amount of time was 33.3 meters per second squared. So that was the linear acceleration of the rock. Next, the angular acceleration of the rock. The angular acceleration. So, we know now the linear acceleration, and we know the radius of the sling. So, we can use our formula that converts between linear and angular. We have linear acceleration equals radius times angular acceleration. So, we just solved for the linear acceleration. We can plug in 33.3. That is going to be equal to the radius of our sling, which is 0.35 meters, times angular acceleration. And that will inform us that our angular acceleration during this time, the rock's angular acceleration, was 95.14 radians per second squared. Radians per second squared. Next question. What was the centripetal acceleration of the stone? The centripetal acceleration of the stone. I'm going to erase these little names right here to make space for the next piece of work. Centripetal acceleration of the stone. So, we have a new formula for centripetal acceleration. That's equal to velocity squared over r. Now, this is the velocity the stone was moving at as it was orbiting at 1.5 seconds. So, we want the final velocity from that point in time. So, AC is going to be equal to that velocity squared over the radius of the orbit. So, 50 squared divided by 0.35. Just going to put that into my calculator and then show you how I put it into my calculator, just to show you the best possible way to be able to enter it to avoid any operational errors. Press enter. And that will tell us that the angular acceleration of this rock was 7,142.9 meters per second squared. Now, the reason that we have found all three of these accelerations is to prove that they are not all the same thing. They are not all the same thing. The linear acceleration represents the change in the rock's linear velocity as it is rotating. The angular acceleration represents the change in its angular speed as it rotates. This angular acceleration represents the rate at which the rock was accelerating towards the center of the circle. It is a different value to the other acceleration. That's why they all have different symbols. We have A, we have alpha, and we have AC. All of these accelerations are different. They all have different formulas. Don't mix them up. Last but not least, what was the tension required in the rope, in the sling, to allow all of this to happen? So in order for David to be doing this, he had to be exerting a force on the rope, and the rope had to be pulling in on the stone. So this rope is constantly pulling into the center of the circle to keep the rock moving in this pattern. It has to be exerting some force, and some existing force has to act as the centripetal force. In this particular case, it is the tension in the sling. The tension in the sling is going to pull the stone towards the center at all points and trap it moving in this circle. Now, we know the centripetal acceleration, we know the stone's mass, we want the centripetal force. The tension is acting as the centripetal force right now. So if we want the tension, the force of tension, we need to find the force centripetal, because right now the tension is acting as the centripetal force. There always has to be some existing force acting as the centripetal force. It's going to be equal to the mass of the sling, of the rock, the mass of the rock, which is 0.3 kilograms, times the centripetal acceleration. So 0.3 times 7,142.9. That's going to be 2,142.9 newtons. That's a lot of newtons. It took a lot of force to be able to accelerate this stone like this. They've had a very good swinging arm. So, some practical examples of the centripetal force and centripetal acceleration formulas. Okay, so moving on to slide 9. What this slide shows is more similarities between linear formulas and that we've already talked about and angular formulas. As I said before, every single linear concept that we've discussed so far has some parallel in the angular space, because displacement, velocity, and acceleration all have angular counterparts, and everything else that we've been calculating is based on those things. So the main things we're going to focus on, there's two more topics we're going to focus on in the angular space, and those are going to be what happens when torque becomes angular and what happens when momentum becomes angular. If we move on to slide 10 now, angular force actually has its own unique name, and that is torque. And torque is another one of those things that you've definitely used before in your life. You have definitely interacted with torque. And what happens with torque is, you've all opened doors, you've probably all played baseball, you might have used a crowbar. All of these things utilize torque. And to use torque, what you do is, so I have this ruler right now. Previously, if I was applying a force to this ruler, it's assumed that I'm picking it up by its center of mass. But something different happens if one end of the ruler is fixed in place. So right now I've got a pivot right here on the end, and some distance away from that pivot, I now apply a force. Now, instead of lifting the ruler up or down, I'm going to make the ruler spin. I'm going to create a rotation. And that's what torque is. Torque is defined as exerting a force at some distance from a pivot, and instead of making that object accelerate linearly through 2D space, now it's going to begin accelerating angularly. It's going to start spinning. So, force always has and always will create acceleration. If you apply a force to a mass, it will create an acceleration. But if you apply a force at a radius from some fulcrum, from a pivot point, you will create angular acceleration. You'll make something spin instead of making something accelerate and move in a straight line. Real life places where you have all seen this include opening doors. When you open up a door, say right now this represents a door that you're looking at from above. If the door hinges are on this side where the pivot is, the door knob is always over here. The door knob is always on the opposite side of the door. It's some radius away from the fulcrum. And so, when you pull on the doorknob, you are pulling at a radius from the fulcrum. and it makes the door spin on its hinges. That's torque. You get the same effect when you're playing baseball, because when you actually hit the ball, you are applying that force at a distance from the fulcrum of your hands. So you are using torque to hit the baseball. You also get this effect when you are using tools like wrenches and crowbars. Say, for example, this was a wrench and I had just put it on a bolt that needs tightening. If this is the bolt right here and I'm cranking the wrench, I'm exerting a force on this end of the wrench, some radius away from the fulcrum of the bolt. And that creates torque to make the bolt start rotating. So, torque is a concept you've been using for a very long time. You've been, if nothing else, opening doors for a very long time. And I'm just going to help you put some math and some words to it. So, the formula for torque is on slide 11. The formula is on slide 11. And that formula says that torque, and the formula for torque, the variable for torque that we're starting with here, this is not a normal letter T. This is a tau. This is a lowercase Greek letter tau, because physics ran out of good letters a while ago. Torque is equal to the force that you are applying to an object times the radius that that force is exerted from the object's fulcrum. So the farther away you exert the force, the more torque you're going to get. That's why we have wrenches. The longer the wrench handle, the greater the radius is, the more force, even for the same force, at a bigger radius, you're going to get more torque. So grabbing the end of the wrench is a lot easier than coming up right onto the bolt and trying to make it spin. Because the radius is so much smaller, you're not going to get as much torque. Similarly, I recommend you try this at home. If you try to open a door, first by pulling on the opposite side of the door where the doorknob is, I recommend also trying to open the door by just pushing it a lot closer to the hinges. I'll actually move my camera to show you this. So normally, we're exerting force here on the edge of the door, which is some distance away from the hinge. And that takes a certain amount of force. What I recommend you try is, rather than apply force here on the far side, try to apply force very close to the hinge and feel for yourself how different it feels, how harder it is, because the radius of rotation is not as big and you're not getting as much torque out of the process. So, torque depends on the force you apply and the radius that force is applied from the fulcrum. This is the symbol for torque. It's the Greek letter tau. And something to be aware of, torque is measured in units called newtons times meters. It's newtons times meters. Because to find torque, we multiplied newtons by meters. And that's just the unit for torque. So, moving on to slide 12, we're going to do a quick example of this. We have in this particular scenario a 100 kilogram mass hanging from the end of a 1 meter pole. So this mass is hanging 1 meter away from a fulcrum, and gravity is going to pull down on this mass. Gravity is going to pull down on this mass, and therefore that force is also going to be applied on this rope tied to this pole. So there's going to be a force pulling down on this pole 1 meter away from this pivot right here. and that's going to create a torque. So, question 1, how much torque is produced by the hanging mass? So, part A, we're going to find torque 1. It's going to be equal to the force pulling down on this rod by this mass. Now, the reason that there's going to be a force pulling down is because of gravity. The force pulling down on this mass is going to be equal to gravity. So the force in question is going to be equal to the weight of this object. And the formula we use to find weight is the object's mass times 9.8, and then, so this right here is just the force applied. So the weight of this object is what's going to pull down on the end here. This is how we find that weight. It's mass times 9.8. And then we're going to multiply by the radius from here to here, which is just 1 meter. So, to solve this question, we're going to plug in the mass of this object, which is 100 kilograms. We're going to plug in acceleration due to gravity, which is 9.8. And we are 1 meter from the fulcrum. So, that is going to give us a grand total of 980 Newton meters. So that is the torque produced by this object hanging on the end of this pole this far from the pivot. Now, that torque is going to try to make this rod rotate. It's specifically going to want to make it rotate this way, clockwise. And torque is technically a vector, so we need to make note of the fact that it wants to make the rod spin clockwise. Because we have another force right here pulling up on this cable, pulling up on this rod, trying to keep this thing from rotating. This is trying to keep the post from rotating. These two forces are pointed in opposite directions, and so this hanging mass is trying to make it spin clockwise. This force pulling up is trying to make the post spin counterclockwise. They're going to be in opposite directions. And we want them to balance out. We want one to equal the other. Because if they're even, if the torques are even, the sign is not going to rotate. This post won't rotate if the torques are even. Like how linearly, if all of the forces on an object are balanced, if all the linear forces on an object are balanced, that object won't accelerate. Angularly, if the torques on an object are balanced, that object is not going to angularly accelerate either. So we want the torque created by this force to be the same as the torque created by this force. So our second torque needs to be equal to the value of the first torque. That means we can plug in the same 980 we just found, because we want the torque created by this force to be 980 Newton meters in magnitude, just in the opposite direction. That's going to be equal to the applied force times the radius that that force was applied at. So that force is applied at 35 centimeters away from the pivot. 35 centimeters is going to convert to 0.35 meters. So in order to find the force, we're going to need to divide both sides by 0.35. Put that in my calculator for all of you. So the force required, marker, to hold up this sign, to keep it balanced and keep it from rotating, is 2,800 newtons upwards. Notice this force is a lot bigger than the force of gravity pulling down on this block. The force of gravity on this block would only be about, well, we multiplied by 1 here. We took the force of gravity and we multiplied it by 1. So the weight of this object is going to have the same number on it. Notice then, this force required is much, much bigger. And that's because it's being applied at a smaller radius from the fulcrum. If you want as much torque as possible, you want to apply that force at a very long radius away. This is why for big, heavy-duty jobs, you will find long crowbars and long wrenches to give you more radius, therefore to allow your force to create more torque. Now, let's pause actually. Excuse me. Now, moving on from that example on slide 12, we move on to the next couple of slides. There's one extra formula for torque that I want you to be familiar with. See, this formula here is not the only formula for torque. In fact, most of the other formulas that we have been looking at today are the angular counterparts to their originals. But this is the original formula for force. Force equals mass times acceleration. But this formula is not the angular counterpart to this formula, because this formula contains force and radius, neither of which are the angular counterparts to mass and acceleration. So, the second torque formula is going to be the angular counterpart to this formula. Now, the angular counterpart to force is torque, so we're going to replace that F with our T. The angular counterpart to acceleration, to linear acceleration, is angular acceleration, which looks like a fish. That just leaves mass. The funny thing about mass is, mass also has an angular counterpart. And that angular counterpart is called moment of inertia. And that is represented by a capital I. This is the moment of inertia. Now, the reason that mass has an angular counterpart is because an object's tendency to rotate in a particular way depends on a lot of factors about that object and how you are rotating it. So, actually, let me think. Okay. My water bottle is a metal cylinder. It has a certain mass, and assuming I'm not changing the amount of water in it, that mass is going to stay the same. But I can make this water bottle rotate in lots of different ways. I can spin it this way through its cylindrical axis, kind of like if it was rolling. But I can also rotate it like this. I can spin it around like I was spinning a stick. Additionally, I can also spin it like this through the other axis. I can even try to hold on to the end of it and spin it around like it's orbiting a center point. For most objects, there's lots of different ways you can make them spin, and that every single object has a different tendency to spin in a different way. And so, moment of inertia is the angular counterpart to mass. Mass linearly represents an object's tendency to keep moving in straight lines. Moment of inertia represents an object's tendency to rotate and to keep rotating in specific ways. And if you move on to slide 13 has a brief explanation of this. Slide 14 shows a bunch of different objects rotating in different ways. And you find their moments of inertia very differently because they're all separate objects and they're all behaving differently to one another. in all of our sample questions, either you will be given enough information to find the moment of inertia, or you will be given the moment of inertia itself, and you'll be able to use it in the rest of the question. But the main thing that you just need to know for the sake of these formulas is that moment of inertia acts as the angular counterpart to mass. And slide 15 has this formula on it. Slide 16, we're going to use this formula really quickly. So, brief example of using this formula. A wrench has a mass of 15 kilograms and a length of 80 centimeters. And we are going to exert a force of 200 newtons on the end of this wrench. We want to know what the wrench's angular acceleration is going to be. So, this is our wrench. It's going to be spinning about this bolt right here, and we want to know what its angular acceleration is going to be. Now, the formula that we just covered, we have torque, we have moment of inertia, we have angular acceleration. This is what we want to find. We want the angular acceleration of this particular object in this scenario. In order to find that angular acceleration, we're going to need, one, to figure out the torque acting on this wrench, and two, we're going to need to figure out the moment of inertia of the wrench. Let's talk about torque first, because we're just going to use this formula to find that. So, torque equals force times radius. We know the force being applied to the end of this wrench, and we know the radius from the force to the fulcrum. It's going to be 80 centimeters. So, for torque, we can plug in 200 times 80 centimeters. That force times radius is going to be our torque. So I'm plugging that in for torque. Now notice, this is 80 centimeters, which means we're going to need to convert that to 0.8 meters. 80 centimeters becomes 0.8 meters. Next, we need moment of inertia. Now, this is where you can consult that table right there. This wrench, we can consider, for the sake of simplicity, we're going to consider the moment of inertia of this wrench to be the formula that you see on the bottom right, of that table, because that represents a long cylindrical object rotating about its end point. So it is rotating about in a circle around its end, like this. Actually, I'll show you better with, it'll work better with this paper towel roll. So, this wrench, you are going to put it on a bolt and make it start spinning. It's spinning about its end point. It's not spinning about its own center, it's spinning about its end point. It's just a long piece of metal spinning like this. And out of all the objects on that table, the formula that best represents a rough, long, cylindrical piece of metal rotating about its end point is that formula on the bottom right. And just to summarize that formula on the board, it says that the moment of inertia for such an object would be equal to 1/3 times its mass times its length. Is that squared? Squared. So, the moment of inertia of this wrench will be equal to 1/3 times the wrench's mass times its length squared. So, for I, we can plug in 1/3 times its mass, which is 15 kilograms, times its length, its length is 80 centimeters. That's going to be 0.8 meters, and that term is going to be squared. And then the only term left is our acceleration. It's the only one left. So now we can solve for it. I'm going to simplify this one step at a time. I'm going to combine the 200 and the 0.8 together. That's going to give me 160. Next, I'm going to multiply these three terms into one another. So that's going to be 1 divided by 3 times 15 times 0.8, and make sure you are only squaring the 0.8. Notice how I put that in my calculator. That's going to be equal to 3.2 times alpha. So now to get alpha by itself, we're going to divide both sides by 3.2. And so our angular acceleration, our alpha, is going to be equal to 50 radians per second squared. 50 radians per second squared. So, moment of inertia is the angular counterpart to mass, and either you will be given enough information to find it, or you'll be given the moment of inertia and you'll be told what you can do with that information based on the question. Every question is going to have a slightly different kind of object in it, and so you're going to need to consult this table in the notes to tell you what formula you need for that shape and how it is rotating. Okay, now the last thing we're going to talk about today, and this is the last concept that is an angular counterpart to something we've talked about linearly, is angular momentum. Now, momentum, linearly, is an object's tendency to keep moving as it is in a direction with a velocity, and how hard it is to make it stop. And angular momentum is very similarly, but rather than its tendency to move in a straight line, this is its tendency to keep spinning. If you have ever been, actually, decent example, this armchair, this office chair. If I make it spin, its mass now has an angular velocity. It's going to want to maintain that angular velocity. It's going to keep moving at some speed if it was completely left alone, like how an object flying through space left by itself would keep flying forever. Now on Earth we have friction that we have to deal with, so I have to keep pushing it every so often, but the chair wants to keep moving. And if I want to stop it, I have to exert some effort to do so. If the chair was spinning faster, I would have to push harder to stop it. If it had more mass, I would have to push harder to stop it. So, angular momentum is a lot like linear momentum, just replace moving forwards with spinning. And you can observe this if you spin a wheel and just watch it. It wants to keep going, and it takes effort to make it stop. But one other thing we're going to talk about today, and this is true of both linear and angular momentum, momentum tends to be conserved in an interaction. So, the thing about linear momentum is it depends on linear mass and linear velocity. And an object's linear mass can't really change. If an object is moving, it's going to keep its same mass, because if its mass changes, it lost part of itself and it's no longer really the same object. But the thing with angular momentum, and we've got the formulas up on the board here, this is linear momentum and this is its angular counterpart. So the angular counterpart to mass is moment of inertia, the angular counterpart to velocity is angular velocity, and the angular counterpart to momentum is angular momentum. The variable for that is an L. Again, I'm not really sure why. We ran out of good letters a while ago. And the unit for angular momentum, we are multiplying angular velocity by moment of inertia, and so the standard unit that we're going to go with is kilograms times radians per second squared. Nope, sorry, not squared, just radians per second, excuse me. Now, the thing about moment of inertia is it depends on how an object's spinning, it depends on its mass, and it also depends on the object's radius. So moment of inertia of a single object can actually change if the object begins spinning differently, or if somehow its radius changes. And an example of that, if you've ever, and you can do this at home if you have your own office chair or a similar chair that spins. If you are sitting in the chair and you spin it while you're sitting in it, or you have someone else spin it while you're sitting in it, and you have your arms and legs splayed out in all directions very far away from you, that is increasing the radius over which your mass is distributed. So right now you have a very large moment of inertia. You've distributed your mass over a very large radius. So if you spin the chair with your limbs out, you'll be spinning at a specific velocity based on your moment of inertia. Now, you can actually change your moment of inertia by changing the radius at which your arms and legs are splayed out. So, if I pull my arms in, if I pull my arms in and I avoid kicking the wall, I'm going to spin in the other direction now because I'm getting dizzy. So if I pull my arms and legs in, it might have been a little subtle, but without even touching the wall or kicking off of anything, I got faster. I'm going to do it again. I'm going to get up to speed, and then I'm going to pull my arms and legs in. Okay? And pull. I encourage you to try this at home, because it's a lot easier to feel than it is to see me doing it in here like this. So, get some kind of chair that spins, sit in it with your arms and legs out, have someone spin it with you in the chair, and then, once you get a feel for how fast you're going, pull in your arms and legs and see if you can feel the difference. So since moment of inertia can change if the object changes its radius, that means that the object will still have the same amount of angular momentum, because no outside force has actually come in to change that. You will still have the same amount because no outside force has tried to stop you. You'll still have the same angular momentum, but now that your moment of inertia has changed, your angular velocity needs to change by a similar amount in order to keep your angular momentum the same. And an example of this, if you look, so slide 17 shows these formulas. Slide 18 sort of shows a picture example of what I just described. Notice in both cases, the L is the same size because there's still the same amount of angular momentum in the system. No outside force has changed the amount of angular momentum in the system. But as the person in the chair pulls in their arms and reduces their moment of inertia, their angular velocity has to increase in order for the system to maintain its angular momentum. And that's what this formula right here means. If there is no outside force on a system, its initial angular momentum will be the same as its final angular momentum. Now we're going to use that and show that in one quick practice problem. A person sitting on a chair has a total mass of 85 kilograms. So we're going to say mass of 85. Initially, their arms are held out to a radius of 1 meter. So our initial radius is 1 meter. And they are rotating, so their initial angular velocity is 1 radian per second. Eventually they're going to pull in their arms, so you're going to have a final radius of 0.5 meter. And we want to find the final angular velocity. So, we have the formula for angular momentum right here. Angular momentum equals moment of inertia times angular velocity. So, the initial angular momentum is going to be equal to the initial moment of inertia times the initial angular velocity. And that's going to be equal to the final moment of inertia times the final angular velocity. So this is what we want. We know the original moment of inertia. We know the original angular velocity. So now we just need to figure out what we're going to plug in for moment of inertia. Now if you move on to the next slide, slide 20, I put the chart in again a little bit bigger, and for the sake of simplicity, we're going to assume that the person spinning on this chair is most similar to the solid cylinder or disc. That is the middle entry on the left. And that entry says that the moment of inertia for a solid cylinder or disc spinning about its central axis, its central lengthwise axis, is equal to 1/2 times its mass times its radius squared. And I'm basing my assumption on what type of shape it is by just, if I look at this chair and I spin it, out of all these shapes, it's sort of forming a more cylinder shape, and it's rotating about its central point. So we're going to assume that this person's moment of inertia is akin to that of a cylinder. So this is the formula for moment of inertia we're going to plug in on each side. So the initial moment of inertia is going to be 1/2 times the mass times the initial radius squared times the initial angular velocity, which is 1, equal to 1/2 times the mass times the final angular velocity squared. No, wait. Sorry. My mistake. Times the final radius squared, which is 0.5 meters, and then times the final angular velocity. This is the term that we want to solve for. And the only thing that we don't know now is the final angular velocity, so we should be set to go. Now, I'm going to simplify this a tiny bit first, because on both sides we have a 1/2 and we have a mass. Since that's on both sides, they can cancel. Additionally, 1 squared is just 1, and that 1 is being multiplied by 1. So everything on this side is just going to condense down to 1. This 0.5 is being squared. 0.5 squared is going to be 0.25. So we got 1 equals 0.25 times our final angular velocity. We're going to divide both sides by 0.25. So our final angular velocity is going to be equal to 1 divided by 0.25, and that's going to be 4 radians per second. So by pulling in their arms, this person has quadrupled their spinning speed. And this is mathematical proof of the fact that if you pull your limbs in, you will go faster. So that is every concept that we are going to relate into the angular space, into the angular reality. Please go back over these notes as needed. Review the PowerPoint. Please ask me questions. Come to our calls with questions. And this will go up with the new homework at the same time. Now we're going to start one more chapter before we start going into our first test. So stay tuned for information about that. And thank you all, and have a great day.